I'm presenting, and with the source code which is available on GitHub, maybe even reproduce them if you like. So I ran all benchmarks on a DGX2 with important thing 16 Tesla V100, which are, I need to, is there? No, there is no laser pointer. Which are NV switch connected so that they can all talk at full bandwidth to each other. As an example, I use a Jacobi solver for the 2D Laplace equation on a rectangle. You don't really need to follow the math. I think I hope I explained that simplified enough so that you can map that when I'm presenting to your own problem. But for those who are familiar with it, I'm using directly boundary conditions, so constant values on the left and right boundaries, and periodic boundary conditions on the top and bottom boundary. So let's map that to code so that those who don't know what that is actually see what we are doing. Essentially, we are computing a simple while loop which checks for convergence in every iteration. And in every iteration, we do a Jacobi step, which iterates over all interior points of a domain, essentially calculating the average of an old array and storing that to a new array. Then we apply the boundary conditions, which in case of the left and right is just do nothing because that are directly boundary conditions, so the values stay constant. But top and bottom is periodic boundary conditions, and that is emulated by copying the first row modified to the bottom boundary and copying the last row modified to the top boundary. So I'm never touching the boundaries because the average always takes the all the neighbors. So I'm only computing on the interior ones, the dark green dots here. Then we swap the role of A and A new and start the next iteration. So very simple one, but the basic communication patterns are translating over to more realistic, more complicated stencil codes. So if we want to do this multiple GPUs, in this case I've chosen to apply the domain decomposition strategy, which is the usual strategy to parallelize these kind of codes, as most of you probably know. And quickly summarizing different ways we have to do the domain decomposition on these 2D problems. So first we could aim for minimizing the number of neighbors, which is good for latency-bound communication because we need to communicate with less neighbors, and that would result in splitting our domain in stripes. So depending on how our data layout is, it's better to have horizontal stripes, for example, if it's in row major order, in C codes mostly, or in vertical stripes if the data is in column major order, for example, in many Fortran codes. If we are in a bandwidth bound regime, it's better to minimize the amount of data we are communicating, and that can be done by minimizing the surface area to volume ratio, and that can be done achieved with tiles. So here I want to keep the code simple and explain the different programming models. So I'm selected the horizontal stripes as the domain decomposition, and that is applied like this to our code. So logically, the only thing what changes is that we are now not iterating over each GPU is not iterating over all interior points, but only over the ones assigned to it, but always over full rows. After that, we are applying the periodic boundary conditions, and we need to exchange data with our top and bottom neighbors to propagate information. So that how that happens is that these interior boundaries, we call halos, are replicated across the neighboring nodes, so that the first inner row GPU I is computing is the bottom boundary of the top neighbor of that GPU. So nice thing now is that the applying of periodic boundary condition in a single GPU case is essentially the same as we are doing with this halo update. If we treating the last GPU as the top neighbor of the first GPU and the first GPU as the bottom neighbor of the last GPU. The rest stays the same, so After we did that, we swap A and A new, and then start the next iteration. It's all that simple because we are reading only from A and we are writing to A new, so we can execute all this in arbitrary orders, massively parallel, so works quite nicely. So let's start with the first variant. So assume you cannot use any threading and only can use CUDA. How would a single-threaded multi-GPU version of this look? So it's a lot of code, but I will walk through that step by step. So we have the, at the top, we have the while loop, which we also would have in the serial version. And within each iteration of the while loop, we loop over all devices. We compute the top and bottom neighbor for that device, which is if the device is larger than 0, the top neighbor is just my device ID minus 1. And if my device ID is smaller than none devices minus 1, it's just my device ID plus 1, and otherwise I wrap around with this model operation. Then we select to issue the next instructions to the device which has currently its turn. And then this does its local operation. It resets the level 2 norm value, it starts the local Jacobi kernel, and it copies back the norm. So that's just this loop in the middle. After that, we need to do this halo exchange, and that is done with two memcopy async, and because that's the fundamental communication pattern here. I want to dive a bit deeper into that and explain how that works. So the first memcopy sends the first row we have modified to the bottom boundary of the top GPU. This is why the A new array there is indexed with the top. And the next map copy, which happens at the same time, sends the last row we have modified to the bottom boundary. And since that is a push to our neighbors, at the same time we are receiving from our bottom or our top neighbor the rows. So the data is propagated, we have exchanged the interior boundaries, the halos, and also applied periodic boundary conditions. So let's look at performance of this. For that, I want to highlight one thing, that I'm using application clocks here to control GPU boost, because I didn't want to run my performance test for a very long time. And if I'm not doing that, I see that the dynamic boosting of the clocks have an effect on spinning up the clocks. And I want my results, I don't want my results to be disturbed by that. Realistic simulations would run for such a long time that this is not noticeable. So in case you want to reproduce the numbers, I'm pointing that out. So that I'm setting the application clocks to the highest possible value. This code can run safely at that, so it can sustain that clocks, which essentially defines the floor for the GPU boost if no terminal or power budget violations occur. Another thing before I look at multi-GPU performance is what problem size should we look at? I want to look at strong scaling, so we keep a fixed problem size and then scale it on from 1 to 16 GPUs on the DGX2. But we want to compare the different multi-GPU programming models, and I don't want to have the results disturbed with the effect that the local domain size gets too small to actually run at full performance. Therefore, I started with a single GPU performance test where I increased the problem size and then selected the problem size where 1/16 at least delivered 99% of the best performance I got. And that happens to be 18,432. So if I take that squared, divided by 16, I'm larger than the 4069, where I'm still running at 99% of peak performance. So we're looking at strong scaling, maybe not in the, but in a regime where the scaling limiter will not be the local problem size. Okay, so That's how we selected the problem size, what is the benchmark setup. Now let's look at results, and what results are we looking at. Some metrics for success. I'm measuring the serial time. I'm measuring serial time in the sense that it's just using a single GPU. It's of course still a parallel program. Then the parallel time with multiple GPUs. And from that we can calculate the speed up by dividing the serial time with the parallel time, where optimal speed up is obviously P. So with P GPUs we can expect to run P times faster. And also derive the efficiency by dividing the actual speed up with the optimal one, and there the efficiency is, the best efficiency is obviously 100%. So, first result with a single-threaded multi-GPU version. Adding GPUs, we see that runtime gets slower, but it quickly levels out, and our parallel efficiency at 16 GPU is quite poor at only 36%. On every slide where I present numbers, there's the benchmark setup given at the bottom. So as said, the code is available on GitHub, so you could try that out yourself if you have access to a DGX2, of course. So the question is, why are we not achieving better? 36% parallel efficiency is obviously not great, so it would not make much sense to scale this far. For that, obvious tool is to use our profiling tools and look at the timeline first. And this was zoomed into the transition between two iterations. And what we see here is our mem copies caused by the halo exchanges. And you see they're all in the rows of host device and device to host copies. Like you might remember, on the DGX2 we have NVLink, so why are there host to device, device to host copies? Although we could use NVLink for more efficient communication. And because we can access the memory of one GPU directly from another one, avoiding these staging through the host memory, which increases the bandwidth. The reason is that if that's enabled, it comes with overhead for certain operations, so it is an opt-in feature. So we need to enable this peer access so that it is utilized by CUDA mem copies, and we can use direct load stores to peer GPU memory. And that is done by calling CUDA device enable peer access to another device. So for every device, we check if it can access its top neighbor. If it can access it, we activate that access. We check if it can access its bottom neighbor. If it's not the same as the top neighbor, in case we run with two GPUs, do the same check there, and then enable the peer access. If we do that, rerun, and take a look at the timeline again, we see now we no longer have some device to host copies. That's because we are copying back the norm. But the bulk of the copies are now peer-to-peer copies, and the gap between two iterations actually gets shorter. And we see the effect of that when looking at the parallel efficiency and comparing that to the initial version. So it went up to 38%, better, but still not great. So definitely not job done. So looking at the timeline again, we cannot really obviously improve the copying here. So let's take a look next why these the kernels are not starting all at the same time. So we're almost seeing 100 microseconds between the first and between the start time of the first kernel on the first GPU and the last kernel on the last GPU. So instead we're currently using a single CPU thread. So these all operate independently, and we have multiple CPU cores on a DGX2. So why not assign one CPU thread per core? And I've chosen to use OpenMP for that. You could also use pthreads directly, or Intel thread building block, or whatever you like to do. And I start exactly one thread per device. So I first, before I spawn my threads, I query how many devices are there. Then I start a parallel region with the number of threads matching the number of devices. And in the parallel region, I need to assign CPU threads to GPUs, and I just do that by taking the thread ID of OpenMP and use that to select the device. Rest of the code stays the same, except that I don't have the for loop in the while loop, and I need a little bit of thread coordination between them. So looking at the performance of that, that is actually quite a jump. So from the single-threaded copy with peer-to-peer, peer-to-peer is of course also enabled, we're up now at 77% parallel efficiency with 16 GPUs. So we're definitely not done yet, as you might imagine looking at the watch. So what's the gap? Here we still see the copies here, but now the difference is getting, the difference, the startup time is getting much closer, but there's still a little bit of wiggling. That is and we have a gap. So I will introduce two optimizations, but I will start with the less important one, just for, because it's easier to carry forward on that didactically. So let's first take a look at the wiggling, because we can address that by pinning our threads. For that, I want to show you the topology of the DGX2, which I'm using, which you can query with NVIDIA SMI topo-m, which gives you this nice matrix where you can see how the GPUs are connected to each other. In this case, it's every GPU is connected with 6 NV links, where NV switch to every other GPU. And it also gives you the affinity to the CPU cores, so to which CPU sockets the GPUs are close to. So the first 8 GPUs are connected to CPU socket 0, second 8 GPUs are connected to CPU socket 1. So an obvious for to pin your threads is then to pin your the threads controlling the first 8 GPUs to the first socket, and pin your threads controlling the second 8 GPUs to the second socket. Like you could, for example, do it with these quite verbose OpenMP environment variables. However, which makes sense, and it might make sense for your application if you have bigger amounts of host and device transfers in every iteration. But in the case we are looking at here, it's actually better to pin all threads to the same socket, because for the performance, the inter-CPU thread performance, communication performance, is more important than being close to the GPU that is controlled. So if we apply that, we see a slight increase in performance from 77 to 79% parallel efficiency with 16 GPUs, and also an effect that the runtime difference when the kernel startup is getting smaller. So next step is minimizing the gap between, which is caused by the communication. As I told you initially, this is a massively parallel problem, so it doesn't matter in which order we are processing our interior domain. So we could just split it up into a boundary part, which we are processing first, just the first row and just the last row, and an inner domain. The nice thing is that to communicate with our neighbors, we only need the first and the last row. We don't need the interior points. And therefore, the bulk of the processing is in the inner of the domain, and we can do the mem copies for the data exchange with our top and bottom neighbor while we are computing the bulk, while we are doing the bulk of the work. There are different ways to do that. One I'm showing here at the example of OpenMP. The other I will show later as the example of MPI. So this one is also a lot of text. Here I'm using high priority streams for communication and computation overlap, because it gives me the opportunity to hide more CPU work launching kernels. So first we start computing the bulk kernel, which is the first block here. So And the stream wait event is to wait for the copies of the last iteration before we start the next one. So that was also in there, if you check the